This is a supplementary video for Lecture 8, Part 2, where we will solve all the leftover exercises in the homework exercise set 5. So we will start from number 3, and we need to match the graph of each function in Part A through Part D with the graph of its derivative in Part 1 to Part 4. And we need to give reasons for our choices. All right, so the graph of A looks like this. This is graph of B, and this is graph of C, and this is graph of D. And the correspondingly, graph 1, graph 2, and graph 3, and graph 4, we need to match up with each graph over here. Okay, so before getting into this problem, let's just recall a few conceptual points. So first, if F has horizontal tangent at the number x, so this implies f prime of x takes 0. So this another thing is if f has a corner point, f has corner at x. So this will also tell me that f prime of x does not exist. And the other thing you need to know is if the tangent, the slope of tangent is large, so this is actually going to tell me that f prime of x is large. So these are the 3 conceptual points that will help us to tackle this problem. Okay, so for part A, if you look at the slope of tangents, you can see that the slope of tangent is going to be negative to the left of this point, positive to the right of this point, and between these two until it hits this point. And finally, it will be negative again when x gets larger. And moreover, the horizontal tangent existed at these 2 points. So namely at these 2 points, well, the derivative takes 0. All right, so let's actually look at these 4 graphs. So where do we have 0 derivatives over here? You can see that the graph of these guys, well, only these 2 graphs has got intersections to the x-axis. But notice over here, so this graph over here, this means the number 3 over here means f prime of 0 will also have to be 0. But over here, we do not have got a horizontal tangent at 0. So this means A can only be matched with number 2. So let's just write down our solution here. So part A, the derivative will have got a graph as 2. Well, another feature is just like you see that it will be to the left of this point, the slope is negative. And between these 2 points, the slopes are positive. And finally, to the right of this point, the slope becomes negative again. So this is another match towards what we have analyzed before. Okay, so for part B, well, you could see that there are 2 corner points over here. Whenever we have corner points at x, so f prime of x does not exist. All right, so then you see that only part 4 matches up the description. So you see that the derivative does not exist at these 2 points. And moreover, you can see that well, the slope of the tangent are actually kind of constant between these points. So as a result, the derivative of f of x are just like horizontal over here. So for this graph in part B, it should be matched up with number 4. Okay, so for part C, we see that there is a horizontal tangent at the point 0. And moreover, for all the other points, well, the slope of tangent is non-zero. Well, there's no other horizontal tangent over here. And well, to the right of 0, the slope is positive. To the left of 0, the slope is negative. And the only graph that matches up is going to be this one. So you have got the slope is 0 at the point 0. And then to the right of 0, well, the slope is all positive, although it's actually getting smaller and smaller. It's getting close to 0. So, and to the left of 0, well, the slopes are negative, and it's going to be getting close to 0 as x gets negatively large. So for part C, the graph you should match up with is going to be part 1. Finally, for part D, well, that's the only remaining choice, but that's still analyze what's going on. So you see that there are 3 horizontal tangents over here. So this corresponds to 3 0 points in the graph of f prime of x. And between the first and the second point, so the slope is negative, so correspond to this part. Between the second and the third point, the slope is positive, corresponding to this part. And finally, after the third point, it's going to become negative, so corresponding to this part. And before the first point, well, the slopes are all positive, so corresponding to this part. All right, so that's how these two graphs are matched together. All right, so that concludes problem 3. Now let's investigate problem 42 and 44. So for these two problems, you are given the graph of f, and you need to state with reasons the numbers at which f is not differentiable. Okay, so first recall the following conceptual points. So when is f not differentiable? So there might be the following cases. So first, if f is not continuous at the number x, so this will tell me that f prime of x does not exist. So the second possibility is f has a corner point or a cusp point. So in this case, well, f prime of x does not exist. All right, so these are basically two conceptual points, and you need to know about this problem. Let's look at problem 42. So you see that the graph is not continuous at this point. So let me keep track of it. So f is not continuous at x equals to -1. So, and moreover, you could see over here, so this kind of point is called the cusp point in a sense that the tangent is kind of vertical over here. So this is what we call the cusp point. Usually when we call the corner point, this means well, the tangent to the left and to the right, they looks like they are not that vertical, but still the slopes to the left and to the right of the points are completely different. So this is what a corner point is. Cusp point can be viewed as a special case of corner point, but then I would still prefer to separate the notion like this. Okay, so coming back to the problem. So for problem 42, so we can see that f has a cusp point at x equals to 2. So then, well, from this observation, we conclude that f is not differentiable at x equals to -1 and x equals to positive 2. All right, so that solves the problem 42. Okay, so for problem 44, you could see that there are two corner points, one at x equals to -2, the other at x equals to 3. So these points are corner points. So as a result, the function is not differentiable at these 2 points. Besides, there is a discontinuity at the number 1. Therefore, those are the 3 points where the function is not differentiable. Now let's write that down. So first, f is not continuous at x equals to 1. Moreover, it has corner points at x equals to -2 and positive 3. So as a result, f is not differentiable at x equals to -2, positive 1, and positive 3. All right, so that concludes number 44. Problem 61. So we need to sketch the graph of the function f of x equals to x times absolute value of x. And we need to determine for what values of x is f differentiable. And finally, we need to find a formula for f prime. Okay, so remember the standard technique for us to deal with absolute value is to write it as a piecewise function. Let's start by doing that. So first, recall that if x is greater or equals to 0, then in this case, absolute value of x equals to x. So this will imply me that f of x in this case is going to be x times x itself. Well, this is just the absolute value removed. And then what we get is x squared. All right, so this is what happens when x is greater or equals to 0. On the other hand, if x is strictly less than 0, so in this case, absolute value of x equals to -x. So f of x is going to be equals to x times negative x, and the answer will be negative x squared. So to summarize, well, my f of x is now written as a piecewise function. So it will take positive x squared when x is strictly greater than 0 or equals to 0. So it will take negative x squared when x is strictly less than 0. Okay, so based on this, we can attempt to draw the graph for this piecewise function. So this is going to be my xy coordinate, and we know that f of x equals to x squared basically looks like this. But then because originally we have got a parabola that's this looking like this, but because we only need the part when x is greater or equals to 0, so that's why we are only keeping the right hand side over here. On the other hand, for the other side, well, f of x equals to minus x squared looks like this originally, but because we only need the part when x is less than 0, so that's why we only need this part. All right, so this will be the graph for this f of x. So let's supplement the x and y axis. And finally, let's just mark that this is the curve y equals to f of x. All right, so this will be the solution to part A. So for part B, there is an important conceptual point that I would like to emphasize over here. So let me just write some comments in green. So in the test, you do not need to write these words. So for part B, we will have to determine if the limit of f of x plus h minus f of x divided by h as h approaches 0, we need to determine if this guy exists or not. Okay, so we certainly know what this guy is. Well, we have already got a formula. So as long as we know if x is positive or x is negative or x is equals to 0, we know what f of x is. But how do we determine f of x plus h? So this is the problem for us. So the problem is, what should we use for f of x plus h? Okay, so I will address this conceptual point in this problem. So here is the important observation. So the observation is, if x is strictly greater than 0 and h is sufficiently close to 0, so in this case, we say that x plus h is also strictly greater than 0. Okay, so this can be seen from the following picture. So let's say that this is going to be my 0 and this is going to be my x on the number line. So if my h is sufficiently close to 0, then I can control my interval to be sufficiently small. And the interval can be controlled to be so small that every member inside this interval, namely every possible choice of x plus h, is going to be sitting to the right of the number 0. So in other words, if we are interested in the limit that involves x plus h and my h is approaching 0, then my x plus h can always be taken to be strictly positive. And as a result, we will say that f of x plus h is going to be x plus h squared. All right, so this is the first observation. And a similar observation exists when x is strictly less than 0. So let me just copy the comment here and then just make modifications afterwards. So what I should have is, if x is strictly less than 0, so, and moreover, if my h is sufficiently close to 0, so in this case, I can also say that x plus h will be strictly less than 0. And why is that the case? Well, in this case, well, with my x, I started with an x that is strictly less than 0. Then if let my h to be sufficiently small, then you could see that every possible choice of x plus h will be to the left of 0. So in that case, x plus h is going to be less than 0. Therefore, my f of x plus h will now be taken as minus x plus h. All right. So these are the two cases when f of x plus h does not have any ambiguities. Okay, but be very careful over here because there's one other case that we haven't been able to solve. The other case if x equals to 0. So in this case, well, the same does not hold anymore because if x equals to 0, let me just copy my graph down here. So if x equals to 0, so then you could see that it's really depending on what h is. So if x equals to 0, so then you will see that no matter how small you choose this interval, well, there will be numbers that's to the left and to the right of 0. So in this case, f of x plus h depends on the sign of h in this case. All right, so let's actually write that down very carefully. So if x equals to 0 and h is sufficiently close to 0, together with h to be strictly positive. So in this case, we just use f of 0 plus h as positive h squared. On the other hand, if we have got h to be less than 0, so that way we have got f of 0 plus h will have to be minus h squared. So this is why when we were discussing the limit of a piecewise function at the critical number, so in this case, the critical number is 0. So then we always need to discuss the left-hand limit and the right-hand limit of the function because, well, to the left of 0 and to the right of 0, well, the function is defined differently, as you could see from this example. Okay, so this is basically how we determined the f of x plus h over here. In the test, this analysis is not necessary. You do not need to write down the details over here. So I will show you what to write over here. So for part B, if x is strictly greater than 0, then the limit of h approaches 0 of f of x plus h minus f of x over h. So you could directly say that f of x plus h equals to x plus h squared. You do not need to provide justification for this step. Well, but you should be very clear about the conceptual points we just mentioned before, but then you could, when in practice, you could simply write f of x plus h equals x plus h squared without any justification. All right, so then you compute this limit by yourself. So we have seen this limit a lot of times, and I will skip the computation over here. So at the end of the day, you will get positive 2x. So in particular, this tells me that f prime of x equals to 2x if x is strictly greater than 0. So in particular, this is also telling me that f is differentiable when x is strictly positive. All right, so similarly, if x is negative, then limit of f of x plus h minus f of x divided by h as h approaches 0. So now you just use what we have discussed before. So f of x being minus x squared and f of x plus h, well, this is being minus x plus h squared. Okay, and the whole thing is divided by h. And again, you could do the computation by yourself, and at the end of the day, what you will get is minus 2x. So in particular, this is telling me that f prime of x equals to minus 2x if x is strictly negative. Okay, finally, let's look at what happens if x equals to 0. If x equals to 0, so that in this case, well, we saw in the previous slide that it's really depending on whether or not h is greater than 0 or h is less than 0. In other words, we need to look at the right-hand limit and the left-hand limits. So let's look at the right-hand limit. So what we have is going to be f of 0 plus h minus f of 0 divided by h. Well, what is my f of 0? My f of 0 is pretty easy. So this guy is simply 0. So this follows from our formula over here. So f of x, if x equals to 0, then f of 0 is going to be equals to 0 squared, which is going to be 0. How about my f of 0 plus h? Now, because we know that h is approaching 0 from above, So this is going to be f of h, where h is greater than 0. So we are supposed to use the same definition over here again to say that this is going to be equals to h squared minus 0 divided by h. All right, so what I'm getting at is going to be the limit of h as h approaches 0, and the answer will be 0. All right, so this is the right-hand limit. And on the other hand, the left-hand limit. So for the left-hand limit of f of 0 plus h minus f of 0, so you see that f of 0 is still the same. So this is still going to be equal to 0. However, f of 0 plus h, so this guy is now f of h, but then because h is less than 0, so that's why I should take f of h equals to minus h squared in order to be consistent with my formula over here. All right, so that's why I have got minus h squared divided by h over here. So then what we will get is the limit of minus h as h approaches 0. And well, from here, we could see that the limit is also going to be 0. All right, so we see that the left-hand limit and the right-hand limit of the same expression, well, they are the same. So in particular, this implies that the f prime of 0 being the both side limit of f of 0 plus h minus f of 0 divided by h. So this exists, and moreover, this guy equals to 0. Okay, so from here, we have concluded that if x is positive, f prime of x exists. If x is negative, f prime of x exists. And finally, if x equals to 0, f prime of x also exists. All right, so then, so to answer part B, so what we can say is actually, so f is differentiable everywhere. So that will be the answer for part B. And for part C, so we just write down the formula. So f of x equals to 2x when x is strictly greater than 0. And it will be minus 2x when x is strictly less than 0. All right, so if you want, you could certainly write f of x equals to 0 when x equals to 0. But then you could see that this is really does, you do not need to actually write in this way. Indeed, if you set the first one equals to 0, so then you see that the formula also gives you 0. So then this will be simplify the answer to f prime of x. So namely f prime of x, it will be equals to 2x when x is greater or equals to 0, and it will be minus 2x when x is strictly less than 0. Or actually, if you are careful enough, you could observe that this is precisely the same as 2 times absolute value of x. So if you want the formula for the f prime of x, then this is going to be the most simplified formula for f prime. Okay, so this is the discussion of problem 61. But the observation we have discussed over here, so these observations hold for all the piecewise functions. So more precisely, we can summarize everything orally as follows. So if x is a geometric number that does not coincide with the critical number of the piecewise function, then for f of x and f of x plus h, well, you just use the same formulas as we have seen here. So for, well, x less greater than 0 is a generic number, so that means f of x plus h follows the same formula over here. On the other hand, x less than 0 is also a generic number, so in this case, you just use this formula also for f of x plus h. Okay, but if x is a critical number for this piecewise function, so then, well, depending on the left-hand limit and the right-hand limit, you probably need to use one formula or the other formula. So really depending on what limit you are discussing. So this principle applies to all piecewise functions, and we will see a few more examples in this video.